Okay, now we're going to look at comparing two populations and comparing their correlations side by side. So what I want to do is, so what do we have? Researchers are wondering whether the size of a person's brain was related to the individual's mental capacity. They selected a sample of 5 females and 5 males and measured their MRI counts and IQ scores. The data is reported to the right. Complete parts A through D. Okay. So first, a scatter diagram treating MRI count as explanatory and IQ as a response. So let's open our data in StatCrunch, just as we did before. Now, right now, I have we have our data in 2 columns. I want to create a scatter plot with everything on it. I don't think I can do that without moving the data around. X variable, I'm going to have to, what I'm going to do is do a copy, Control X copies, or that cuts, and then paste is Control V on a PC, on running Windows, I mean. Anyway, this is the males and the females. I'm all combined into one. I'm going to separate it out a little later, but for now, let's see what the combined scatter plot would look like. My X variable, I want to have MRI, female MRI, although it's actually not just female, it's all MRIs. And IQ is the response variable because it says we're trying to predict IQ score based on MRI. Okay, so you can see what we have. The MRI is on the x-axis, we have IQ on the y-axis, and we have this pattern here. It looks very much like choice C. Let's get a closer look. We've got, it's very faint, but you can see the dots match up in the same places. IQ, MRI down below, everything looks good. So it's choice C. All right, compute the linear correlation coefficient between MRI count and IQ. Are MRI count and IQ linearly related? So we're going to go back to this. We're going to go to stat, summary stat, correlation, and we're going to take those two. At this point, we're not breaking the population into subpopulations of male and female. We're just looking at what is the correlation between them. Okay, it says it's 0.703. That would round up to 0.704. Is that strong enough? Let's go back here. We have a sample size of 10. This table of critical values says a sample size of 10, we need a correlation coefficient to be at least as strong as 0.632. That is strong enough. 0.703 is bigger, so I'm going to say yes, we are linearly correlated. But remember, I'm going to have to round up 0.704. And now we're going to see how this breaks down between the males and females. So I'm going to in order to get a scatter plot with the different colors, I have to do a little bit of manipulating of the data. So what I'm going to say is have sex in the in this other column, and I'll have F, 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 F for the first 5, and then M, oops, M, 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 let's fix that, M. Okay, let's just call this MRI. And let's just call this column IQ. So what I'm going to do when I graph this now, graph a scatter plot, I'm going to still select MRI to be on the x-axis, IQ to be on the y-axis, but I'm going to group by sex. And when I do that, I have grouping options. I'm going to color the points by group label. What that's going to mean is that I'm going to get all of the female points are going to be in one color, male points in another. Right now, I don't know what colors it's going to use by default, but that's fine. We'll just let it go and see what it comes up with. It'll pick two different colors. It'll tell me what they are. So you can see what we got. We've got the blue for the female and the red for the male. So it looks like from this data set, the males tend to have higher MRI scores and higher IQs. Females have lower MRI scores and lower IQs. But this is just data that was made up for this problem, right? So let's now don't get confused by the coloring. It looks like the default colorings are a little different in these examples. This one looks close, but it has IQ on the x-axis. We need MRI on the x-axis, so let's pick this one and just take a look. Okay, so it's very hard to see. We've got these dots, but yes, indeed, they're in the right place. The colors aren't specified, but it's clear that that's the right one. So I'm going to go with choice B. Okay, so now I'm going to separately calculate the correlation coefficient for males and females. So I'm going to go to summary stats for correlation, and I'm going to still do MRI and IQ, but now I'm going to group by sex. So what I'm going to get now is two correlation coefficients, one for males and one for females. Here we go. Isn't that beautiful? So for females, the correlation coefficient 0.119. For males, negative 0.217, rounding up. So if we go back to the critical values necessary to state that there is a significant correlation between the two variables, now we have only 5 males and 5 females. For a sample size of 5, you need a correlation coefficient to be greater than 0.878 in absolute value. These are both smaller than that in absolute value, right? They're pretty close to 0, and so I would say because the correlation coefficient for females is it's positive, right? And the absolute value of this correlation coefficient is 0.119. I'm still taking 3 decimal places. Is not greater than, what was that number again? Let's pull up the table. For a sample size of 5, 0.878. Okay, 0.878. It's not greater than 0.878. No relation exists between MRI count and IQ for females, because the correlation coefficient for males is negative, and the absolute value of this correlation coefficient is, let's type it in, absolute value, I leave off the negative sign, 217. This is, again, not greater than the critical value for the male data set. And again, because the sample size is 5 for males and for females, 878. And I'm going to say no relation exists between MRI count and IQ for males. Great.